Okay, electronegativity and bond polarity. So Lewis' theory is very nice and simple, but you kind of realize it couldn't be that simple, right? Showing the electrons as dots is actually a drastic oversimplification. When the electrons are shared between two atoms, they are not necessarily shared equally. In fact, they are usually not shared equally. So what's known as a polar covalent bond is a bond where you have one or more pairs of electrons that are shared between the two atoms, but they're not shared equally. So here, hydrogen fluoride, we've got the hydrogen and we've got a fluorine. We're not showing the lone pairs, we're just looking at the bond. And so this pair of electrons shared between hydrogen and fluorine, actually the fluorine kind of hogs the electrons. And so those electrons spend more time around the fluorine than they do around the hydrogen. So the electrons are negative, and if the electrons are spending more time around the fluorine, then this end of that molecule is going to be a little bit negative. It's not an ionic bond. The electrons haven't been transferred, but they're not being shared equally. If you've ever slept with another person, whether it was a sister or a significant other or a brother or whatever, you know about the blankets, right? There's always that one person, and it's never you, right? It's the other person that just hogs the blankets, right? Okay, so that's what's going on here. One of them is a blanket hog, an electron hog, okay? So then one person's nice and warm and one person's cold, right? So we've got the negative and the positive. So we represent that in different ways. So one way is like this, where we've got the hydrogen and this covalent bond with fluorine, and the arrow has a cross at this one end, so it's like a plus sign. So the plus is at the side that's more positive, and the arrow points to the blanket hog. Or we can represent it this way with a lowercase Greek delta. It looks like a D with posture issues, slouching D. So delta positive and delta negative. That stands for a partial positive charge and a partial negative charge. If this was ionic, it would be +1 and -1. But it's partial, so it might be +1/3 and -1/3, or something like that. So here's another analogy I have for this. The electrons being little boys, right? And the atoms being homes. So there's hydrogen is one house, and fluorine is the neighbor's house. And this bond is two little boys that are playing together, right? And, kids play together. They'll go over to this house or that house. They'll be in this yard or that yard. Well, sometimes one house is more appealing to little boys, right? So hydrogen's house, they have an old black and white CRT television. They've got a VCR and some old banged up Thomas the Tank Engine VHS tapes. Yuck, right? They've got tap water. They don't even have ice in the freezer. And if you're hungry, Mom will give you a couple pieces of bread. She's stingy with the peanut butter even, okay? So the kids are not going to spend a whole lot of time over there. Over at Florian's house, they've got a big screen TV. They've got all the game systems. They've got satellite TV. If you're thirsty, they have a soda fountain in the kitchen. I mean, how cool is that? They've got a pool in the backyard, a trampoline. Mom will order pizza in if you just even look hungry, right? Where are those kids going to spend most of their time? At the Florian house. Why? It's more attractive, right? It's more attractive. So they're going to spend more time over here. They are still being shared. That pair of little boys is occasionally going to go over to Hydrogen's house, just check in with Mom, maybe get some clean chonies or something, but they're going to spend most of their time over here. And this arrow I think of as a neighbor, and Dad comes home from work and says, "Where are the guys?" And the neighbor points, "They're over there." So this is the neighbor pointing, they're over at Florian's house. So the arrow goes to the more electronegative element. I realize that some of these analogies are maybe a little too detailed This is what goes on in my brain. They just get more elaborate every semester. Does that make sense, though? Yeah. Okay, so this is what would happen if you put polar molecules with a polar covalent bond, between charged plates. So here we've got two metal plates, but there's no charge on the plates, and so these are going to be oriented randomly because there's no reason for them to line up. If we apply a voltage across and make this plate negative, wait, that one's positive, can't see. This one's positive, this one's negative. This is electrically negative. The positive end of the molecules will be attracted to this side, the negative to the positive side. And so this can be observed. You can get the molecules to all line up if you put a charge on the plates. So that's what a polar compound will do. So electronegativity is a measure of how attractive that atom is to electrons in a chemical bond. So fluorine is very electronegative. It's the coolest place for those little boys to hang out. And among the elements, fluorine is the most electronegative. There are others that are pretty cool, but they're not quite as cool as fluorine. Electronegativity is inversely related to atomic size. So as an atom gets larger, it becomes less electronegative because of that distance factor. So fluorine's the most electronegative. The noble gases are so unreactive, and electronegativity talks about the ability of an atom to attract electrons in a chemical bond. Well, the noble gases don't really make chemical bonds, so we can't really talk about them in terms of how attractive they are to electrons in a chemical bond. So we just leave them out, okay? So here's sort of a three-dimensional representation of electronegativities in the periodic table. So the taller the column, the more electronegative. So here's fluorine, king of the hill, right? The most electronegative. So this was given a numerical scale, and they said, well, 4.0 is going to be the most electronegative, 0 would be the least. It's kind of like a grade point average, right? So fluorine's got a 4.0. And as you move away from fluorine in any direction, the electronegativity drops off. There's a general trend. There are some exceptions in the trend, just like we saw some exceptions in the trends for atomic size and ionization energy and all of those sorts of things. But we can predict relative electronegativities in the same way as we did the other trends. Now you'll notice that there are some elements that have the same electronegativity. So nitrogen is 3.0 and chlorine is also 3.0. So there are elements that will have the same electronegativities. Unless you are given a table like this or specific values for electronegativities, I do not expect you to remember those, okay? So if you have two nonmetals that are not the same element, I would expect you to make an educated guess that their electronegativities are not the same, because most of the time that's true. You know, if I said, well, oxygen and selenium, they're different. You name almost any two pairs and they're going to be different. Just a couple that are the same, like carbon and sulfur, but you don't need to remember that. So a polar bond is an unequal sharing. Now, the example I gave of hydrogen and fluorine, that's like an extreme thing, right? It's more typical, thinking of the analogy with little boys, that one house is just a little cooler. And so then they're going to spend their time more equally, maybe not exactly equally, because maybe this mom's nicer or something. You know, she doesn't fuss at you when you track dirt on the carpet. And so the boys are going to go over there more often. But it's going to be more equally shared. And so there's a continuum from completely equal to so extreme that the one house actually adopts the kid from the other one. That would be Ionic, right? So he just like leaves his home and he comes over and he lives permanently with these guys over here. That's the extreme. So we have a continuum here. So we can look at the difference in electronegativity. We often represent that as, come on, pointer, delta En. So delta meaning difference, and En short for electronegativity, because that's a really long word. So at one end, we've got equal sharing or close to equal sharing. In the middle, we've got sharing, but it's not equal. And at this extreme, we have the ionic bond where the electron is actually transferred from one to the other, and it's not being shared at all. And so you've got this continuum, and so we have to kind of make a division. What are we going to call nonpolar, meaning they're shared equally? There's not one end that's different than the other. And the word polar relates to the north and south pole, right? The Earth has a north pole and a south pole, even though it's a sphere, right? So we say, you know, from one end of the Earth to the other, how can you have an end of a sphere, right? But one end has a magnetic field that's different from the other end. And so there's a difference from one end to the other. And that's what we're doing with the polar bonds. So covalent means the electrons are shared. Polar means not shared equally. One end is different than the other. So in between, we have electrons shared unequally. And so the division is, if the difference in electronegativity is above 0.4, is going to be a polar bond, meaning it's not shared equally, up to about a difference of 2.0. At that point, the difference is so extreme that we have an ionic compound. Okay, so those are divisions that we have made, and we just kind of agree on them. You might run into questions where you have to use those numbers in like a homework problem. I won't give you any questions on an exam about those. And so this is what I want you to remember for an exam and for your future classes in chemistry. So we need to be able to predict, is it a polar or a nonpolar covalent bond, or is it an ionic bond? So ionic, I got to choose a pen. Ionic bond, what do we need for an ionic bond? What kind of elements? A metal and a nonmetal. So we've got metal, nonmetal. So if you've got that situation, it's ionic. We're not talking about covalent or anything, because the metal will give up an electron, the nonmetal takes it, and then you've got opposite charges. So if we have a nonpolar covalent, the book sometimes uses pure covalent. I don't like that. I call them nonpolar, because we got polar and nonpolar. Polar covalent is going to happen if you have identical elements So a nitrogen molecule, 2 nitrogen atoms. Well, they're both nitrogen. They're the same. So their electronegativities are the same. The difference between them is 0. That's going to be a nonpolar bond. So anytime you have 2 of the same element, nonpolar. The one thing that I want you to remember is carbon and hydrogen. The difference between carbon and hydrogen is small enough that it's considered nonpolar. So let's go back and look at that one. Whoops, too far. So here's carbon, 2.5. Here's hydrogen, 2.1. The difference is 0.4. It's right on the line, but it's considered a nonpolar bond. Okay? The reason I want you to remember that one is because carbon-hydrogen bonds come up a lot in organic chemistry. And in organic chemistry, it's very important to be able to say this is polar, this is nonpolar, this is a polar bond, these are nonpolar bonds, because that has a big effect on how reactions occur. So because it's so common, I want you to remember that one. So if you've got a carbon-hydrogen bond, it's nonpolar. So for the polar bonds, for polar covalent, two nonmetals that aren't the same. So two different nonmetals. And the one exception there is carbon-hydrogen. So if you've got carbon and chlorine, would that be a polar bond? Are they different? Yeah, that's going to be a polar bond. If you have chlorine and chlorine, polar or nonpolar? Nonpolar, because they're the same, right? They're the same. If you have calcium and chlorine, ionic, metal, nonmetal. Okay? Does this always work? No, there are some exceptions, but those exceptions don't come up very much, and this is a lot easier than even trying to remember what those numbers are, the 2.0 and the 0.4. This will get you through most of what you need. So dipole moment is how we can measure bond polarity. We talked about, okay, well, this is more polar or less polar. You get some quantitation, you can quantitate it. So it's called the dipole moment. It's given the symbol mu. And the dipole moment occurs anytime you have a separation of positive and negative charge. So in a polar bond, you have a separation of positive and negative charge. So the dipole moment is equal to Q, where that's the charge magnitude times the distance r. And a common unit is the debye. A debye is 3.34 times 10 to the minus 29 coulombs times meters. We're not going to really do anything with that unit, but I want you to at least have heard of it for any future classes that you might take. So we can look at these compounds or these molecules here. And for Cl2, we've talked about that one. That should be nonpolar, right? The difference in electronegativity is 0 because the atoms are the same element. And so the dipole moment is 0. It's completely nonpolar. Chlorine and fluorine, are those the same element? No. So we would predict that that's a polar compound, right? A polar bond. The difference in electronegativity happens to be 1.0, and the dipole moment is 0.88. So the dipole moment often ends up being similar to the difference in electronegativity, but it's not necessarily the same. Hydrogen and fluorine. Just from my rule of thumb list, should that be polar or nonpolar? Polar. Two nonmetals. Remember, hydrogen's hanging out over there with lithium and beryllium, but hydrogen is not a metal. It's an explosive gas. It's a nonmetal. Difference in electronegativity between hydrogen and fluorine is 1.9. It's almost ionic, but not quite. 1.9, and so it also has a larger dipole moment. Lithium fluoride, what kind of a compound is that? Ionic, metal, nonmetal. So here, the electronegativity difference is larger. It's 3.0. And the dipole moment goes way up. Any questions? There's also another way to think of this as percent ionic character. So an ion would be, we completely transfer the electron. A polar bond is, well, it's not transferred, but it's hanging out over here more often. So it's sort of like, what percentage of the time do the boys spend at this one house? So the percent ionic character, ratio of the actual dipole moment to the dipole moment it would have if the electron was completely transferred. And so what we see is that there's actually no bond that is 100% ionic. We think of them that way because it's good enough and it's a lot easier. So up here we have all of these ionic compounds, right? Here's their percent ionic character, and here's the difference in electronegativity. As the difference in electronegativity gets larger, percent ionic character gets larger. But none of them are actually 100% ionic. So we should know that, but for the most part we're saying, no, it's transferred, it belongs to this other guy, they've adopted him. So for percent ionic character, the dividing line between a polar covalent bond and an ionic bond is 50%. So here's 50, and we see 50% hydrogen fluoride is up here. It's really close to being ionic, but it isn't. And all of the guys up here are metals and nonmetals. All of the things below are just nonmetals. Any questions? So we should be able to answer questions like this. Identify bonds between these two atoms. Is it pure covalent? So I'm going to change that. Is it nonpolar covalent? Is it polar covalent, or is it ionic? So iodine and iodine. Nonpolar. Those are the same atom. They have the same electronegativity. How about cesium and bromine? Ionic. Why? Metal, nonmetal. Phosphorus and oxygen. Polar covalent. Two nonmetals, but they're different. Okay?